37. Did you guys notice this morning, if you're driving out when it was dark outside, did you guys notice how
I couldn't,
you can't see the light very well?
yeah, all my bus was coming to pick me up. I couldn't see, like, I didn't calculate the bus, and just like the headlights, I couldn't see any of the other lights.
Yeah, so that's a cool thing. We actually call that the Tyndall effect in science. So when that light comes through the atmosphere, normally it doesn't have any water in the air, but if you put a bunch of water in there, that light gets blocked and then it bounces off, and it's really cool because you can't really see stuff. It's weird. Okay, so how thermal energy and temperature are related to each other. So different objects at the same temperature can have different amounts of thermal energy, right? And it all has to do with that mass that we saw yesterday. When things change state. So if enough thermal energy is transferred, it can cause substances to change state. We know that. Something's ice, we add energy to it. I can get those molecules to have more energy. They can release and they can turn into liquid, just like you guys see, those icicles melting. So during a change of state, the thermal energy changes, but the temperature can technically stay the same. This is such a weird thing, and I'm not going to lie, I had to read it quite a few times when I was doing the lecture notes because my brain's like, that doesn't make any sense. But the last fact, which maybe I should have had that in red too, that's really the whole reason why. So the average kinetic energy of the molecules does not change. So even though when you see these icicles melting, I see some of these are going to have higher kinetic energy, on average, they don't. So that's why the temperature stays the same, because that's literally what the temperature is. It's the average. So on page 143, on the top, when you get done writing that, let's just answer this question quick. So in figure 2, we can see these icicles melting. Icicles melt as their thermal energy increases. So we add energy to them, they're going to start melting. However, the temperature of the melting icicles stays at 0 degrees Celsius, because remember, that's what freezing is in the Celsius scale. Think about the difference between thermal energy and temperature. How might the melting icicles gain energy without changing temperature? How might they change or increase energy without changing temperature? So why don't you go ahead and answer that question on page 143. Like I said, I hope by the end of this chapter we'll be like absolute experts on the difference between thermal energy, heat, and temperature. If you need to ask the person sitting next to you, feel free to ask the person sitting next to you. Did you guys know you can read your textbook too to find answers? Did anyone know that? No. That? Yeah, that's one thing I feel bad about making notes for you guys.
I was just testing.
All right, anyone want to answer? Anyone think they know the answer? How might the melting icicles gain energy without changing the temperature? Jaden.
I believe the only temperature change would be in the water, because of all that gain thermal energy as it changes to a liquid, it goes off the solid, and the solid won't have any change state. I don't know.
No, that's good. You're on the right track. So average of all of this, because remember, that's really what the energy is, right? The thermal energy. The average is still going to stay that. Some of them are going to get going faster and turn into liquid, but average kinetic energy doesn't change. So it's literally almost kind of like my little facts that I put on the bottom of the slide there. Okay, on page 144, if you guys flip it. Have you ever broken a piece of ice? I think most of us have, even if it's in our kitchen. You may have noticed that the break has angular edges instead of soft ones. This is because of the rigid, organized arrangement of its particles. The model shows the arrangement of water particles in a piece of solid ice just before it starts to melt. So when it's ice, it has this beautiful sort of like repeating pattern, crystalline pattern when it's ice. In the empty circle, draw what the particles would look like after the ice has begun melting. Then write a caption for your drawing that describes what it shows. So this first one on the top here, we see a nice orderly arrangement of those water molecules when they're ice. Water particles in solid form have a rigid arrangement. So I want you to draw down here in the bottom, what do you think they're gonna look like? And each one of these little guys is water. That's a water, that's a water, that's a water. This is actually an oxygen and then 2 hydrogens. Oxygen, 2 hydrogens. When this turns into a liquid, do these things split up? No, they are still the same. They're still the same. When water melts, you're not changing that. It is still, you would have still down here an oxygen with 2 hydrogens attached to it. We actually say water looks like a Mickey Mouse molecule, and you can see why, because it literally looks like Mickey Mouse ears. So these things in your picture down here on the bottom should still be collectively water molecules, but are they going to be in this nice repeating pattern? No. So draw down there on the bottom what it would look like in liquid. Make sure you label here on the bottom. And then answer questions 1 and 2, and I'll give you guys a few minutes to do that one. So it's so important to remember when things change state, when they change phases, if I go from a liquid to solid, solid to a gas, you don't change what they are. They're just changing their arrangement. That's all they're doing. How are they arranged? Water is still water. So when you guys are drawing that picture, are you drawing it where it's totally a new liquid, or are you drawing it where it's partially solid, partially liquid? Partially? Okay, and the reason I'm asking you that is that affects your answer for number 1, right? So what is the temperature of the water in both images? So just like we saw in the icicles in the last one, if it's partially melting, what do you think the temperature would then be if it's just partially melting? It should be 0 degrees Celsius. But if you're a person, I maybe would have drawn that all straight up liquid, me, and that's fine, I don't care. If I'm all liquid, what would it be? What would the temperature be? It would be greater than 0 degrees Celsius, right? You could just do greater than if you wanted to that way. How does thermal energy compare in those? and once again, it's also different based on how you guys drew it. If it's partially melting, what would thermal energy be like? Pretty much the same, right? But if it's totally melted, what would it be? I would say it would be more, right? It would be higher if it's totally. Those molecules would be moving faster. They would have more thermal energy. Okay, do you guys have any questions on page 144? Good? So the more particles an object has at a given temperature, the more thermal energy it has. So here we see, we have a glass teapot, and then we have a glass cup of tea. They're both at 85 degrees Celsius, so they have the exact same temperature. So both of their molecules on average are moving the same. Who has more thermal energy? It's gotta be this, right? This liter pot full of tea has more thermal energy because it has more matter. Because remember, that's what thermal energy is. It's like a math problem. It's a sum, add. So on page 145, underneath the exact same picture that I have up here on the board, if you wanted to cool both the pot and the cup of tea to 80 degrees Celsius, which one would take longer to cool down? The teapot. It's got more matter. The teapot. I mean, imagine summertime comes and let's say you have a normal pool at your house and then you have a kiddie-sized pool. You fill them up with both same temperature of water. Which one's going to take longer to come to, normal temperature so you don't freeze to death when you jump in the water? Big pool, right? It's got more matter. So here's the cool thing too. A lot of this stuff you guys already know. If you just kind of stop and just think about it and think about normal life, daily stuff, you'll actually be like, okay, that makes sense. You don't even know how long it took me to find a good picture of burritos. You would think that there is an easy picture of burritos out there. It's not. It does. I know. And it took me a while to find it. I did type in, I won't lie, when I typed it in, I typed in Chipotle burritos. And that's not, you can get a burrito that looks like that at Chipotle, but most people's don't look like that because you have add other stuff in there. But okay, so an object's change in temperature is going to depend upon what's happening in the environment and the types and the amounts of matter in the object. So how we change the temperature in things is going to depend upon the environment, what type of matter, and how much matter do you have. So the reason I picked burritos is because that goes along with the question at the bottom of page 145. So the question says, suppose you heat 2 bean burritos with the same ingredients in the microwave. And those are not literally bean burritos. Maybe they have a little bit of refried beans in them. If you do that, it pretty feels like you're asking to burn your mouth. Ugh. Anyways. You heat 2 of them up, same ingredients. One of the burritos weighs 0.3 pounds. The other burrito weighs 0.4 pounds. After microwaving each of them for a minute, which one's going to be hotter? 0.3 or 0.4? 0.3, why? Less matter to heat up. Imagine that. Imagine taking a big giant burrito that you buy at the store, put it in the microwave, and let's say you buy a tiny one, like maybe it's a small breakfast burrito or something. You put them in the microwave, you heat them up. We all know the smaller one's going to be hotter. It does not have as much matter. More matter, I got to put more energy in it to get it up to temperature. Should have put a breakfast one in there since we're closer to breakfast time. All right, before we do the lesson check there, on page 147, they have this cool thing about glass blowing there. So on page 147, you see this guy here doing this glass blowing thing. This stuff, for some reason, this has always just absolutely fascinated me. This is such an absolute art. Like, there's a cool show on Netflix where they actually have a contest where people sit and do this. I don't know what it's called. No, it's not. Well, Fortune Fire is where they make knives and swords and whatnot. I forget what the glass blowing one is called, but it's literally like, it's the same deal. It's a competition. Yeah, it's super cool. I'll look it up in a second. How do you think this colorful glass vase and bowl were made? It turns out that making something this beautiful is a result of heat transfer. Glass objects such as these are formed by a technique called glass blowing. So what you see in that picture there, that tube that guy has, literally has a hole in it. So they will literally like blow air in from the one side in order to get air inside that glass that they're making. The process involves a very hot oven to soften the glass. A glass blower can then shape the glass because it's so pliable. It literally turns almost into like putty, silly putty. Consider the transfer of energy happening here. The heat from an oven or torch is transferred to the glass, causing the glass particles to move faster. As the particles move faster and faster, the glass softens. Once the glass is flexible, glass blowers blow air into it, forcing the glass to expand and change shape. So I just found like a short video here on them making some glass, which is cool. So this is a picture they're going to make. Just heating up old glass, melting it is all they did first. Handle. Looks super easy, huh? Yeah. If you want to, I don't know if if they technically have a name for that, but if you want to do that someday, like we're talking like years of an internship to get to the level of what you just saw in there. Jade.
The show's called Blown Away.
Blown Away. That makes sense, right? Since they're blowing glass. The stuff they make on there is just bizarre. It's so cool. Okay, on page 146, we're going to do the lesson 1 check today. By the way, we're going to do the assessment tomorrow on this. Obviously, makes sense, right? So lesson 1 check. Let me just look through the questions here, see if there's anything totally challenging for us. I don't think so. Just make sure on number 8 where it says draw a diagram, make sure you guys are drawing a diagram. So anytime it says that, draw a picture. We don't have to be artist of the year, but do your best. And then if it says label things, make sure you guys go ahead and label those things. Okay, we're going to do that. What time are we at right now? 28. All right, I think what we may do, if you get done with that, why don't you start, I think I have a worksheet in there. Oh, I didn't even put the stuff in there yet. I will put a worksheet in Schoology that I want you to start if you get done with the lesson 1 check, okay? I will put it in there. I haven't put it in there yet. It'll be in this chapter. I just didn't put it in there.